So this part of the lecture is going to be about groundwater. Groundwater makes up about 0.6% of all of the world's water. The source of groundwater is precipitation that goes into the ground. The word infiltrate means sinking into or going into. So we say precipitation that infiltrates the ground. But that's your main source of groundwater, is precipitation. So groundwater is water that fills open spaces in rocks, sediment, and soil beneath the Earth's surface. When precipitation infiltrates the ground, it seeps downward into spaces called pore spaces. So in rocks, the pore spaces could be in fractures, cracks, or air bubbles, which we called vesicles when we talked about volcanic rocks. When we have loose sediments below ground, the pore spaces are the spaces between pebbles and sand and whatever sediments are down there. And when we have soils, the spaces between the soil particles are the pore spaces. So there are different factors that affect infiltration. So we're talking about factors that affect the amount of precipitation that'll seep into the ground rather than precipitation becoming runoff and then ending up in a river, which is surface water, not groundwater. So climate, temperate and tropical regions receive more precipitation, therefore more potential for infiltration. The slope of the land. Steep slopes, you're going to have more runoff and less infiltration, so less groundwater recharge. Soil and rock type. For example, pebbly soil can absorb more water more quickly than clay-rich soil. That's just an example. Vegetation, plants absorb water and will lessen the amounts of runoff on land, allowing for more infiltration. Land use, that's referring to how we use our land. So is there a paved parking lot or is there a grassy field? And then the degree of saturation of the ground. So land that is already saturated can't hold any more water in it. So any more precipitation that hits the land that's already saturated is going to become runoff. So not all earth materials are equal in letting groundwater pass through them. What types of earth materials would be the most efficient at allowing groundwater to pass through? We can think about clay, pebbles, sandy, clayey, pebbly mixes. So in order to answer this question, we need to consider a couple of properties of the materials. How much space is available within the material, called porosity, and how easily does water move through the material? And this is called permeability. So porosity is the percent of a material's total volume that is pore space. In other words, it's a measure of the empty spaces between the particles. So here is a bunch of sand underneath the ground. And here is cement in between some of the sand grains. That tells us this is a sandstone. But you do have some spaces in this rock, and they're able to be filled in with water. So you would take like the whole volume and you would look at what percent of that volume is made up of these spaces where it could fill in with water. And that percent is your porosity. So what factors affect porosity of loose sediment? Porosity is going to depend on the particle shape and sorting. So we're talking about well-sorted versus poorly sorted sediments. We'll talk about the sorting first and then talk about shape. So porosity is highest when all the sediment clasts are equal in size. Pore sorting allows for the smaller particles to settle in the pore spaces, so that lessens the porosity. So this on the left is well sorted. The grains are all around the same size. So that's high porosity. And then over here, the sediments are poorly sorted, meaning it's a whole mix of different grain sizes. We talked about that in the sedimentary lecture. And because you have a whole mix of different grain sizes, the smaller particles are filling in some of those pore spaces. So there's less porosity. And then the particle shape, rounded versus angular. So rounded particles, you're going to have more porosity because angular particles, the angles of those particles are able to potentially fit in tightly like puzzle pieces. So the edges are filling in what would otherwise be pore spaces. Okay, they're able to get like more closely compacted together when you have angular particles. So rounded particles have higher porosity. Angular particles, you're going to get lower porosity. And then porosity in bedrock, for example, would be found in fractures. So in this case, you have all these cracks or fractures in this bedrock. And they've been enlarged by a process called dissolution. Solution or dissolution is when calcite in limestone is dissolved by rainwater. Rainwater is naturally slightly acidic. So when the rainwater touches the limestone, like in this picture here, it's able to dissolve the rock a little bit. So the rainwater collects in these cracks and then it chemically weathers and dissolves a little bit of the rock inside these cracks, making the cracks larger over time. So porosity does not depend on the size of the particle though, okay? It only is related to shape and sorting, not size. So in this picture, you have well-sorted sediments that are rounded, okay? So all of these four groupings of sediment grains are well sorted and rounded. So all four of these squares actually have the same porosity. Then we have permeability. That was the second factor that we need to consider when we're talking about water passing through materials. Permeability was the second factor. Again, that's how easy is it for water to pass through a material. Factors that affect permeability include porosity, the size of the pores, and the interconnections of the pores. So porosity we talked about. The size of the pores, the larger pores are going to allow for more permeability. So, for example, clay particles are going to give us a low permeability because the pore spaces in between clay particles are small. Pebbles have larger pore spaces in between, so pebbles are going to be more permeable. Excuse me. Interconnections of pores, that is referring to how connected are the pores. So are there like tunnels that connect the pores from one to another? Or are the pore spaces not connected? One example would be pumice. Pumice has many pore spaces, but they are not connected to each other. So pumice would have a high porosity, but a low permeability because the pores are not connected. So we would describe materials as either permeable or impermeable. So this shows you some pebbles, and someone is pouring some water through the pebbles, and the water is passing through the spaces because the spaces are connected. So the water is passing through. Okay, great. And then here is showing you a close-up of sand grains where the water passes through in between the sand grains, so that's showing you the connectedness, the interconnections between the pore spaces. So then we have terms like aquifer and aquiclude. So an aquifer is a layer that is permeable, that's found beneath the surface, that allows groundwater to pass through easily. So that would be well-sorted and well-rounded sand and gravel. So either loose sand grains or a sandstone even would make a good aquifer. Another type of rock that would make a good aquifer would be limestone that has fractures that were enlarged by solution. Like this. Okay, this type of scenario would allow for holding a lot of water. Okay, this rock would hold a lot of water in the pore spaces. And the water can move through those fractures from one area to another. In aquiclude or in aquitard, those names are pretty interchangeable, prevents groundwater movement. So that's an impermeable layer. So that would be shale, for example, clay layers, igneous and metamorphic rocks, and volcanic rocks. And this is a cross-section of the ground in an area where there are aquifers and aquicludes. So here is an aquifer. So that's probably either gravel or sand or sandstone. And then you have this layer here that is an aquiclude. This is probably a shale layer or a clay layer. So it does not allow water to pass through it easily. So you end up with this aquifer down here being confined. And then here is an aquifer on top of the clay or the shale layer. And then here is a small lens, which is just a little section underground of, let's say, clay, This could be a clay layer, but it's small, so it's a lens. And then you have water accumulate on top of that layer because it's not passing through to go downward. And the same thing over here. So we call that a perched water table. When you have a little bit of a confining layer that catches water on top of it. That's a perched water table. So now we'll take a look at the zones beneath the surface related to groundwater. So the first step is water infiltrating the ground after it rains. The water is going to seep downward through a layer called the zone of aeration. Okay, so the water goes through, passes through, and it goes through the zone of aeration or the unsaturated zone. And small amounts of water is going to get left behind, stuck in between the particles. We call that suspended water. Pore spaces contain mostly air in the zone of aeration. So here you have a close-up of particles, and most of the pore spaces are filled with air. The white is the air. But you do have a little bit of water that sticks behind after the water passes through. It kind of stays behind, sticking in between some of the particles. Again, that's called suspended water. Okay, then the water keeps passing down, and it collects in the zone of saturation. And within the zone of saturation, all of the pore spaces are filled with water. So you have this close up here, all of the pore spaces are filled with water. That's your zone of saturation. Now, the boundary between the zone of aeration and the zone of saturation is called your water table. So right here is your water table. And then just above that water table, you have the capillary fringe. And within the capillary fringe, water could seep upwards a little bit from the saturated zone into the unsaturated zone. And that happens through capillary action or water tension. And you can model this by taking a paper towel and you put the paper towel, you hold it vertically, and you just dip the very, very bottom of the paper towel into a little bit of water. You could actually watch the water travel up the paper towel. And that's through the capillary action. So like the water passes through little by little, climbing upward into the little fibers of the paper towel. So the same thing happens here. Little bits of the water climb upward into the dry pore spaces. So that's your capillary fringe. Okay, and this just summarizes the previous picture. So the water table, the zone of aeration, the suspended water, the zone of saturation, and the capillary fringe. So I just discussed all of that. Okay, so then we have the term recharge. Recharge of groundwater. Recharge is when water is added to the groundwater supply. recharge of groundwater mainly comes from rain and melting snow. In other words, precipitation is your main source of recharge of groundwater. So here you have recharge, where water seeps downward and enters the zone of saturation. Okay, it's mainly precipitation. Discharge is the opposite. Discharge is any process that lowers the water table or water leaving an aquifer. So when groundwater feeds into a river or a lake or a spring and becomes surface water, that is considered groundwater discharge. So in this case, you have a little bit of a dip in the land, right? And this is a slope going downward. So the groundwater intersects with the bottom of this dip here. So the groundwater is going to feed into this area of land, and then it will actually turn into surface water. So it's not like the water disappeared from Earth. It just goes from being groundwater and now it becomes surface water. So that's called a discharge. So now it's surface water and either is a river or a lake, depending on the rest of the landscape. Springs and wells are also related to discharge. So springs form when groundwater intersects the land's surface. So this is one way of having a spring form. So here's a perched water table, like a little clay layer above the main water table. And then the recharged water is going to sit on top of this clay layer. And collect as its own little water table. So that's a perched water table. And then you have this slope in the land. So this part of the perched water table intersects with the ground surface. So the water is able to seep out of the ground and flows down this hill. So that is a spring. Okay, that is a spring. That's one type of spring. So here's another type of spring, and this is not a perched water table. This is just the main water table is intersecting with these fractures in the ground. And then the water is able to pour or seep out of that fracture. Okay, so that's another type of spring. So this is a spring on the wall of part of the Grand Canyon. So if we look really closely, it's like little waterfall, little tiny waterfalls, like little, it's not really a waterfall, but it's a little stream of water coming out of this wall of the Grand Canyon. Okay, so that's a spring. Now springs, sometimes you could see, depending on where you are, if you're like going in a mountainous area on a highway, sometimes you will see water seeping out from the middle of the rocks. So again, depending on where you are, you might see springs coming out. Then we have wells. A well is, in its basic form, a hole dug into the zone of saturation. So when you dig a hole into the zone of saturation, water will seep in to fill the hole. And then you could go and collect that water out of the hole, or you could put a pump and have like pumping equipment pulling that water out. So this is a simple well in Kenya where they dug a hole into sand until it reached the water table, and then you're able to collect that water. Now you can dig a well if you go to the beach. So if you go to the beach and you sit on the sand, you can dig a hole in the sand until you reach water. Now basically when you do that, you're digging a well.